Hi. I broke this presentation up into two recordings because I noticed that there was an error on the converting scores slide, and I wanted to make sure that I corrected that before we moved on. So you're going to have a part 1 and a part 2 to this video lecture on descriptive statistics. And just so you know, we're almost done. We have about 5 more slides to go through, but we do have a lot of math to calculate, so we'll be having some fun with that. We left off talking about taking a set of scores and trying to convert them into scores that everyone could understand, because even though we can force a set of scores into a bell-shaped curve, we want to be able to talk about standard kinds of scores so that everyone on the table knows what we're talking about. So the first set of standard scores, or the 3 sets of standard scores that we're going to look at first, are z-scores, quotients, and t-scores, and then later we'll move to percentile ranks. So let's start with z-scores because we're going to use z-scores for a lot of things, so I want you to get really familiar with this formula. Z-scores use the raw score that we're interested in on a test. So we take the raw score, we subtract the mean score, and we divide that result by the standard deviation. So again, it's the raw score that we're interested in on a test minus the mean of the test divided by the standard deviation of the test. So let's practice this. I'd like you to take a score of 15 on the test that we've been calculating about. So the test that we just did, the mean and standard deviation. And I want you to compute the z-score if you have a score of 15. So you're going to plug in 15 to the formula as the score. You're going to plug in our mean score, which was 20.5. And you're going to divide your result by the standard deviation of the test, which was 4.4. So pause and go ahead and do that. Did you get a z-score of negative 1.25? Well, that's correct. And let's think about it in terms of the bell-shaped curve. If you have that curve available to you, it's in the text, think about where a z-score of negative 1.25 would fall. It's below the mean, right? Because it's a negative. And certainly 15 is below the mean. And in this particular case, it's more than one standard deviation below the mean, because remember, z's have a standard deviation of 1. So negative 1.25 is going to be between 1 and 2 standard deviations below the mean. That raw score of 15, if you look back at our bell-shaped curve, that raw score of 15 is also going to be more than one standard deviation below the mean. So it all begins to make sense, I hope. We can also take that score, that same score of 15, and convert it into a Q-score or quotient. So we talk about IQ scores, intellectual quotients. We talk about academic quotients or AQ scores. We can talk about developmental quotients, DQ scores. Quotients have a mean of 100 and a standard deviation of 15. So a Q-score is equal to 100 plus 15 times the z-score. So now remember, our z-score for a score of 15 on our test was negative 1.25. So plug that into the equation and compute an IQ score on this reading test for the student who got a score of 15. Take a minute to do that. Okay, if you got 81.25, you are correct. And again, think about it on that bell-shaped curve with a mean of 100 and a standard deviation of 15. 81.25 is going to be, if we plug the numbers in, it's going to be more than one standard deviation below the mean. And now we can compute a t-score. T-scores aren't often used, but they are used in the field of academic assessment. And it's important for you to understand what they are, because if people are talking about t-scores and you don't know what they are, you might be thinking about quotient scores, which are more common, and you'll judge a student as being less capable accordingly. So t-scores have a mean of 50 and a standard deviation of 10. And the formula for a t-score is 50 plus 10 times the z-score. So again, with our raw score of 15, why don't you go ahead and compute a t-score by plugging negative 1.25, which was our z-score, into that formula. So take a minute to do that. Did you get 37.5? That's correct. And if you plug that into the bell-shaped curve, you would see that that score too is more than one standard deviation below the mean. It's between 1 and 2 standard deviations below the mean. Now the final thing that we're going to be doing in terms of scores that are commonly talked about is computing percentile ranks. And a percentile rank is simply the percentage of people scoring at or below a given raw score. And in order to do that, we're going to move on to the next slide, which shows you the stat worksheet that you have available to you on Moodle. And what I'd like to do is to take some time to fill in this stat worksheet. And I'm going to get mine out. You'll see at the top of the stat worksheet, number 1 says, draw a normal curve in the space below, segmented by mean and 2 standard deviations above and below the mean. Now, we've had several slides on that, so essentially going back to draw your bell-shaped curve, and then divide it into, first of all, divide it in half, creating a mean, and show mean. X with a line over it, and then draw 1 standard deviation above and 2 standard deviations above, 1 below and 2 below. So go ahead and do that on your worksheet. And once you've drawn your curve, I want you to fill in the percent of cases in each section of the normal curve. So I'm going to go back to this curve here. And remember, between the mean and 1 standard deviation above the mean, we capture about 34% of the scores of the population. And between the mean and 1 standard deviation below the mean, we capture about 34%. So go ahead and write 34 and 34 within 1 standard deviation above and below the mean. Then when you go to between 1 and 2 standard deviations above the mean, we capture about 14%, so go ahead and write 14% there, and do the same on the other side of the bell-shaped curve. Between -1 and -2, it's about 14%. And then if we go 2 above, it's about 2%, and if we go 2 below, it's about 2%. So go ahead and write 2% into each of those sections on your bell-shaped curve. And that's question number 2. So now go ahead and on that curve that you've drawn, go ahead and put in where the z-scores would fall. So fill in the mean and standard deviation by z-scores. Z-scores, remember, have a mean of 0 and a standard deviation of 1. So you're going to have 0 as your middle score, +1 and +2 on the positive side, -1 and -2 on the negative side. So now you should have a bell-shaped curve that has that's divided into standard deviation units, has the percentages filled in for each of the standard deviation units, and then also shows the z-scores at the bottom. So 1 and 2 and -1 and -2. All right? So the next question asks us, what is the percentile rank that goes with each of the z-scores that you've identified in step 3. So, looking at the chart that you've now drawn, what would the percentile rank be for a z-score of -2? I'm going to flip us back up to our bell-shaped curve back here. And if you look over to the left of the curve and we go to -2, -2 would be a z-score. A z-score of -2 standard deviations. How many people or how many scores are at or below that z-score? And again, we're rounding up numbers, remember, and on your curve that you drew, we rounded the numbers. So you should have the number 2 or 2% in that space that is at or below a z-score of -2. Does that make sense? You have that? So you can. So the answer is what percentile rank goes with a z-score of -2? The answer would be a percentile rank of the second or 2 percentiles. The second percentile. Now let's move up the bell-shaped curve a little and go to -1 of a z-score. So -1 standard deviations. A z-score of -1. How many people are captured at or below a z-score of -1? And remember, we're rounding up. So we have 14% in between -2 and -1, and we have 2% below -2. So we have 14 plus 2. So the percentage of everybody at or below a z-score of 1 standard deviation below the mean would be approximately 16%. We're rounding our numbers. Okay, did you get that? So now let's go to our mean of 0. 0 is the mean z-score. So we're right at the middle of the bell-shaped curve, and we want to add up the number of scores or people at or below that mean of 0. And so back to rounding up the numbers, we're going to add 2 plus 14 plus 34. And if you add 2 plus 14 plus 34, you should get 50, or the 50th percentile. So the mean of 0 is at the 50th percentile. It's the score that captures 50% of the scores, or 50% of the population. Conversely, if we go in the other direction, the mean of 0 is capturing 50% above the mean score, adding up 34 plus 14 plus 2. So we've divided the normative curve in half, and we get 50% on each side. So at a score of z, we're at the 50th percentile. We've captured half the scores, or half the people. Now we're going to keep adding, because we're going to go to 1 standard deviation above the mean. And so the percentile rank at 1 standard deviation above the mean is every score at or below the z-score of 1. So we're adding 2 plus 14 plus 34 plus another 34. So we're adding 34 to our 50, and we're getting 84. So at a z-score of 1 standard deviation above the mean, a z-score of 1, we've got a percentile rank of 84%, or the 84th percentile. Now at a z-score of 2, which is 2 standard deviations above the mean, we're going to keep adding. So we had 84. Now we're going to add another 14 to that, and we get 98. So at a z-score of 2, adding 2 plus 14 plus 34 plus 34 plus 14, we get a z-score of 98. So 98% of the people or the scores are at or below a z-score of 2. And then what's left above that is 2%. So if we kept on going, we'd ultimately capture 100% of the people or the scores. So fill that in. On your bell-shaped curve that you've drawn at the top of your page, fill in the percentile ranks that correspond with each z-score. So 2% at -2, 16% at -1, 50% at 0, 84% at +1, and 98% at +2. Fill that all in. We'll go back to our worksheet, or I'll go back to the worksheet. Question number 5 on the worksheet asks you to fill in the percentile rank for z-scores of 0, 0.8, -3.1, and so on. Well, now you should be saying, well, I know what 0 is, but I'm not sure about these other ones. How do I get a percentile rank for that? Well, there is a formula for it, but it's a very long formula, and we're not going to use it. I'm going to give you a break. I've given you on the Moodle downloads, I've given you a cheat sheet, and this is what it looks like. It's called Appendix 2, and it says percentile ranks for z-scores of the normal curve. So take a moment and get out your Appendix 2. You're going to need this. You'll need it on the midterm, so don't lose it. Get out Appendix 2. This is our cheat sheet for computing percentile ranks for various z-scores. Now let me tell you how it works. So let's start with the first one. It asks us to find the percentile rank for a z-score of 0. Well, we already did that. And you have it drawn on your bell-shaped curve at the top of the sheet. And we calculated it because we knew the percentages of scores captured within each standard deviation unit. But we could do it without all that adding by looking at this sheet. And I'm going to look at this sheet, and I find under the column labeled Z, so there are 3 columns labeled Z, I find the Z of 0. So I'm coming down the middle here, and I find a Z of 0. It says 0.0 as the Z score. So a Z score of 0. And I go across towards the right under the column labeled area, and I see 0.500. Okay, 0.500. I'm going to move the decimal point over 2 spaces, so now I have 50.0. So a z-score of 0 is at the 50th percentile. So see, the sheet allowed me to get that answer without doing all of the adding. So now you go ahead and you find a z-score of 0.8. I'm going to do the same thing. Got to put my glasses on so I can see the sheet. Find a z-score of 0.8 and write down what the percentile rank for a z-score of 0.8 would be. Okay, did you get 78.8? That's what I got. So I found the z-score of 0.8, and I went across to the right, and I found 0.788, and I moved my decimal point over 2 spaces, and I got the answer 78.8. So now I'm going to ask you to go ahead and fill in the z-scores for the rest of the numbers that are there. -3.1, -1.8, 2.4, and 1.1. So pause right here and go ahead and fill in those z-scores using Appendix 2. All done? So I'm going to give you the answers so you can check your scores. For a z-score of -3.1, you should have a percentile rank of 0.1. And normally we wouldn't say the 0.1 percentile, but we would say whenever we get less than 1, we would just say less than the first percentile. But the most accurate answer would be the 0.1 percentile. For a z-score of -1.8, your answer should be that's a percentile rank of 3.6. So it's a 3.6 percentile. I tend to round up percentiles because we often don't talk about decimals, although you can be that accurate, but we probably would hear that score being at the 4th percentile. The next one, 2.4, your answer should be the 99.1 percentile, or rounded, that would be the 99th percentile. And then for 1.3, the 86.4 percentile, or the 86th percentile would be the answer. So now go ahead and try to answer number 6. Number 6 is asking you what percent of cases scored above the z-scores of, and you have negative 25, 1.4, negative 1, and 0.6. So what percent scores above? Well, that works pretty much the same way using our appendix 2, but in reverse. And there's two ways to answer these questions. I'll work through the first one with you, and then you can go ahead and do the rest. One way to answer these questions is to find the z-score that you're interested in. So I'm interested in negative 2.5, and I find that on my Appendix 2 sheet. And I go over and I see it's 0.006, move my decimal point over, it's 0.6. So 0.6% of the cases are captured at or below negative 2.5. How many is above that? Well, I'm going to take my 0.6 and I'm going to subtract it from 100. And that should give me, if I subtract 0.6 from 100, that should give me 99.4. Okay, so take that, subtract 0.6 from 100, and you should get 99.4. So 99.4% of the cases are scoring above a z-score of negative 2.5. Now, the simpler way to do it without doing the subtraction, although it might sound complicated at first, the simple way to do it is to remember that the bell-shaped curve is symmetrical. So it's the same on each side. So I can turn it around in a way. And so turning it around, I'm going to say, well, I'm not going to look at negative 2.5. I'm going to go over and look at a positive 2.5. I'm turning the bell-shaped curve around. And I go and I find positive 2.5 on my appendix, and I go over and I see that the area at or below that score is 99.4. So you see, it's the negative 2.5, flip it back, is the percent of cases scoring above that is 99.4. So it works the same. If I go to the actual number, negative 2.5, and I find the percentile there and subtract it from 100, I get the correct answer. Or if I flip it, which means turning it into a positive, and I go over, I find the same answer. So you can do the same with the next one, which is 1.4. Flip it, which would be negative 1.4, and see what answer you get. Or go to 1.4, get your answer and subtract that from 100 and see if those answers are the same. So go ahead and do the next three, okay? Ready? So here's the answers. We already did the first one, which was 99.4. So what percent of cases are captured at or above a z-score of 1.4? The answer is 8.1. What percent of cases are captured at or above a z-score of negative 1.0? That's about 84.1 to be exact. What percent of cases are captured at or above a z-score of 0.6? That would be 27.4 roughly. And again, if you rounded it, that's fine. Now the question is, George receives an IQ score on the Stanford-Binet, which has a mean of 100 and a standard deviation of 16, so keep that in mind. Most IQ scores, or most Q scores, are based on a mean of 100 and a standard deviation of 15. That's almost an absolute. The Stanford-Binet is the only exception to that rule, or one of the only exceptions to that rule. In this case, the standard deviation is 16. His score was 76. What's his percentile rank? I love these kinds of questions. So this is a kind of question you're likely to see on the midterm. And I love it for a couple of reasons, the least of which is that it makes you think. So pause for a minute, take a moment, and see if you can compute George's percentile rank on the Stanford-Binet. Okay, so did you get the answer? What did you need to do? Well, the first thing you need to do, and this is one of the reasons I like this question, is you had to think about what score do I need to have in order to have a percentile rank? Well, you need to have a z-score. So the first thing that you need to do is take George's score of 76 and convert it into a z-score using our formula, which is the score minus the mean divided by the standard deviation. And I'm looking at this worksheet up here, and I see that z is written in there wrong. It should be x minus the mean, so the second x should have the mean line over it. I'll try to correct that on the papers before you download them. So your paper should be correct, even though the slide is wrong. So it's the score minus the mean divided by the standard deviation. 76 minus 100 divided by 16. And you should get for your answer a z-score of negative 1.5. And now you can use Appendix 2, find negative 1.5, and you would get his percentile rank, which is 6.7. He's at the 6.7 percentile. Okay? Did you get that? Good. So here's your bell-shaped curve. And I've plugged in a lot of the different numbers for you. So I've plugged in what you have, and this is from the book basically. So what you have is your percentages under each part of the bell-shaped curve. You have your mean and standard deviation units. This takes you all the way to 4, so if you wanted to go that far, but as I said, we normally wouldn't do that. It shows you percentile ranks. It shows you Stanines, which we're not going to talk too much about, but they're there. It shows you z-scores, and I've given you a place where if you want, you can plug in any other kind of scores like q-scores or t-scores, whatever. So all of these scores are explained to you in your readings. But here's a picture that you should sleep with, because it's really important to understand. And the reason it's important is this. I want to be able to say to you, the student got a Q-score of 85 on this test, a standard Q-score of 85, and I want you to be able to close your eyes and see where that falls on the bell-shaped curve. Remember, Q-scores have a mean of 100 and a standard deviation of 15. So if I close my eyes, I see that score of 85 as being exactly 1 standard deviation below the mean. And now I can say something about the student. If the student got a Q-score of 70, again, I know he's 2 standard deviations below the mean, and that's significant. If he got a Q-score of, let's say, 90, I can place him a little bit below the mean, but right there in the average range. If he got a Q-score of 130, I know he's 2 standard deviations above the mean. So I want to be able to do that with any kind of score, so I instantly know where the student falls on the bell-shaped curve, even if it's in between. So for example, if he got a Q-score of 110, I know that's between the mean and 1 standard deviation above the mean, so I know he's in the average range. I can at least talk about average, above average, significantly above, average, below average, significantly below, and so forth. And the Woodcock-Johnson, for example, not only reports out scores, but they report ranges. So you get those terms, average, below, and above, and so on. So again, important things to remember. So you're the whiz at an IEP meeting. So now we're going to talk about developmental scores. And I mentioned age and grade equivalence earlier when we were talking about the types of conversions that can be made to standard scores. And I think I mentioned that I don't like age or grade equivalence, and I don't. But we talk about them, and they are widely used. So you will often hear test results reported as age and grade equivalents. I don't like them for a number of reasons, but we're still going to talk about them since they are so common. The first thing that you need to know about age and grade equivalence is what we're doing is comparing a child's score to the average performance of a sample of scores at a given age or grade level. Now, we'll see what that means in a moment because we'll be calculating some of that. age is written in one way, grade is written in another way, and that's also important to remember. So on your slide, you see age 4-7, which means 4 years, 7 months of age. So 4-7 is 4 years, 7 months of age. And, months, we have 12 months in a year, so we can't use a decimal point. But for grade, we can use a decimal point because we have 10 school months, essentially. So it's a base of 10. Fourth grade, 7th month would be written with that decimal point, 4.7. So if you see 4-7, it's 4 years, 7 months old. That's an age equivalent. If you see 4.7, it's 4th grade, 7th month. That's a grade equivalent. Very important to remember the difference in how they are written in a test report. The problems with developmental scores have to do with interpolation and extrapolation. Those are two very important words, and I want you to remember them, and I want you to understand what they mean. And I'll be showing you a picture of that in a moment. But essentially, when we get age and grade equivalents, it would be ideal if we could go out and test a group of students in every single age or every single grade level. By that I mean, let's take 4th grade. If I really wanted to know grade equivalence, I would test groups of students at grade 4, 0 month, or the beginning of 4th grade, grade 4, first month into it, grade 4, second month into it, grade 4, third month into it, so that I would have exact scores, exact average scores of students at each points in the 4th grade to record so that I could compare other students to those averages. But frankly, that's impossible. First of all, doing standardizing tests is a really expensive process, but getting students month after month after month and giving them the test and getting average scores would invalidate the tests, and it would be inappropriate and too costly to do. So what test makers do instead is that they will go and test a group of 4th graders. Let's say they test them halfway through the year. So they test 4th grade 5th month, 4.5, 4th grade 5th month. And they get the average score for them. And then they go out and they test a group of 5th graders at 5th grade 5th month, 5.5. So now they have average scores for 4th graders and they have average scores for 5th graders, both halfway through the year, and they connect the dots between them. So they interpolate, they draw a line between 4.5 and 5.5 on a graph, and now they can identify, or they can imagine what scores would be at each point between 4.5 and 5.5. They're imaginary scores because they didn't go and get them, but they are somewhat realistic because there should be a progression between 4.5 and 5.5. We can connect the dots and get some idea of the scores in between. And we could do the same for age level if we wanted to. That's called interpolation. Now, if I'm a test maker, I want a test that's useful for a broad range of students. So let's say, for example, I want a test that could be used for anyone from kindergarten through 8th grade. So it's a good test for middle schoolers. And I have a limited budget. So I'm going to go out and I'm going to get a group of 1st graders halfway through the year, 2nd graders halfway through the year, maybe 4th graders halfway through the year, maybe 6th graders halfway through the year. So now I have 4 data points that I can plot on a graph. The average score for 1st graders, the average score for 2nd graders, the average score for 4th graders, the average score for 6th graders. And I can interpolate, I can draw a line between those scores that I actually gathered. And I can then sort of guesstimate what scores are going to be in between. Even though I didn't test third graders, for example, I can guesstimate what their scores will be because I've drawn a line from second grade to fourth grade. I can kind of pinpoint where third graders would fall in terms of scores. But I want the test to be useful for K through 8, remember? I didn't test kindergartners, but I now have this nice line, and I can calculate the slope of it, and I can extrapolate from first grade down to kindergarten. I don't have a data point for kindergarten, but I have a slope of a line that I can just extend from my first grade data point to kindergarten, to the beginning of kindergarten, and I can guesstimate what those scores are. And I didn't test 7th or 8th graders, but I have a data point for 6th graders, and I have a slope of the line, so I can extend that line out. I can extrapolate that line out to 8th graders. And now I have a set of scores, some of which are real, because I actually did test students in certain groups, and some of which are imaginary, because I interpolated and extrapolated. And there's no way of knowing whether that line is real or not. Now, something I know as a professional is that students don't necessarily progress in nice straight lines. Think about your students who have exited third grade knowing a certain amount of material, come into fourth grade a couple months later and have forgotten everything they know. They didn't necessarily continue from the end of third grade to the beginning of fourth in a nice straight line. They actually did something like this. They probably lost a lot of what they had at the end of third grade, or they've forgotten it. It's not lost completely. So I don't know for sure what their scores would look like at the beginning of fourth grade unless I tested them. I think that academic progression is more like this. It's more of a zigzag line. Kids get information, they plateau for a while, they solidify their information, and they might jump up a whole set of scores, and then they might plateau again. So, and sometimes they drop down because they're learning something new. I think development, although it tends over time to go in a line upward, doesn't go there evenly. It goes like this. So when we interpolate and we extrapolate, we're guessing about scores that may not be true. And the other thing that I don't like, so my second problem with developmental scores, age and grade equivalence, is that they promote typological thinking. So if I say to you, you have a student that is performing on a test in reading at the fourth grade, 7th month level, what are you likely to do? Unless you know about testing and how these numbers work, you're probably going to think, well, I guess I could put this student in an upper fourth grade reader and they'd be able to handle that text. Or I could give the student a subject matter book that's written at the fourth grade or fourth to fifth grade level, and this student would be able to handle that material because that's their tested grade level in reading. Well, in fact, that tested grade level in reading is derived from a score that represents the average score for typical fourth graders in the 7th month of school. And your student may not be the average fourth grader. Maybe your student is actually a third grader, but they're testing at the fourth grade, 7th level. Does that mean that they read like a fourth grader or that they can handle subject matter material like a fourth grader? Not necessarily. Likewise, a student who's in 6th grade who's reading at the fourth grade, 7th month level is not necessarily performing lower in all tasks than what their age expectations would be. They just received the average score of a fourth grade, 7th month student. Now, the fourth grade, 7th month student is likely to have received that score because they're following a developmental progression. Your student in the 6th grade is probably not following that progression. They're probably struggling in reading in some areas and doing okay in reading in other areas, and that leads to their depressed score. They may be doing really well in comprehension because they're good at filling in the blanks, but they're not doing so well in decoding. So they would have a hard time with content texts that were geared to a fourth grade student because decoding the words would be hard for them and the content would be difficult for them if they didn't have the vocabulary. Uh, the same would be true for a younger student in terms of understanding content. So just because you got the same score as the average fourth grader doesn't mean that you look like the average fourth grader or that you function like the average fourth grader. I'll give you a non-academic example to try to illustrate it. When I first started working in the field of special education many years ago, I worked at an institute for individuals who were significantly cognitively impaired, and I worked on what were called at the time the severe and profound wards. So these were individuals with extremely low intellectual capabilities. Certainly on IQ tests, they would measure very, very low, and tested, and if you wanted to give them an age level as a score, their age level might be 6 months or 7 months of age. So in other words, that's how they tested. They tested at the 6-month age level. Well, I worked with adults in those wards, and I often think about this. What does a typical 6-month-old look like versus what did these individuals look like? Developmentally, a 6-month-old can sit up. They're beginning to finger feed a little bit if they've been exposed to food. Oftentimes, they're beginning to crawl, or at least attempting to crawl. They're getting up on all fours. They can raise up on their forearms. They don't talk per se, but they do babble. They turn take with you. They make eye contact. They have social relationships. But they're babies. They need to be carried around because they're not mobile, and they don't have a lot of dexterity yet. So they're not really good at some of the tasks like self-feeding and so on. Even they might hold a bottle independently. But then I think of these young men that I worked with, many of whom were ambulatory. They could walk. Many of whom could feed themselves independently using fork and spoon. And most of whom were I would say young adults, so they were between the ages of 18 and maybe 30. They certainly weren't thinking like a 6-month-old because they also had adult urges. And so to say that they were functioning at the 6-month-old level would be really wrong because they had many things that they can do that were beyond the 6-month level, and they just weren't testing well. So they couldn't answer many questions on a standardized test, so they got low scores. Maybe they didn't talk. Most of them were nonverbal. Their ways of communicating were not ways that are measured on a test, although they had ways of communicating. So to think, typological thinking is thinking that you look like the score you got. Well, they didn't look like the score that they got at all. So we need to avoid thinking about someone as functioning at a particular tested level. They're just scoring the same as the average person at that level. But they might have gotten that score in a very different way from the average person at that level. So now you have a sheet called Test Construction. And I'm going to ask you to take a look at that worksheet. And I'm going to pull out mine. If you look at that worksheet, it has a number of questions on it that I'm going to ask you to think through. That worksheet gives you a set of scores for various age levels. So you have a set of scores for first graders, a set of scores for second graders, a set of scores for third graders, fourth graders, and fifth graders. What I've done for you is gone ahead and I've computed the mean and standard deviation for first, second, and third grade, and also for fifth grade. And I've left fourth grade open for you. One of your homework assignments is going to be to compute the mean and standard deviation for fourth grade students on this particular test. So you get some practice with mean and standard deviation. I want you to have that practice because you may need it for the midterm. And then this sheet asks you to do several different things. The first one is to prepare a graph of scores at each at each age level. So do you remember when I graphed the scores back on well, I'll flip up to it so I can remind you how we did that. Remember, I charted the scores for our reading test. I kind of clustered them by twos. So you might want to think about doing that. Cluster your scores by twos or threes. And I plotted how many students got each particular score. So going back to the worksheet now, I want you to make a graph for each age level. Make a graph of the set of scores at each grade level, similar to the one that I just showed you. So at first grade, you'll take all the scores, cluster them by twos, it'll probably make it easier, and graph how many students got each of the scores that are listed. And do that for second and third, fourth, and fifth grade as well. So what you have is a graph of scores that you can eyeball. And the next question asks you, once you've done that, to compare them to the bell-shaped curve and talk about them in terms of central tendency. So do they look like a bell-shaped curve? And skew. Are they skewed in one way or another? So I want you to think about that. So pause here, take the time to graph those scores, and think about the central tendencies of those scores. Remember, I told you to look in the book and really understand what skew and kurtosis and all those kinds of things meant. And then jot down for each of the graphs a brief description of what kind of a curve it is. Okay? Take a moment to do that and then come back. So ready? If you graph the scores correctly and you look at the scores for first grade, you will see that first grade has a positive skew. In other words, the scores clustered down towards the low end with fewer and fewer and fewer students getting high scores. And so we would call that a positively skewed distribution. And one way to interpret that distribution would be to suggest that this test is kind of hard for first graders. It doesn't have enough easy questions on it to distinguish amongst first graders to give us that bell-shaped curve. It's just too hard. Very few students do well on it. Or first graders in this school aren't very capable. I tend to think the test is probably too hard. If we look at second grade and you plotted that set of scores, you would see that this looks somewhat like a normal distribution. It does tend to be lower on each side, comes up in the middle, and goes down. If you smooth it out, it begins to look like a bell-shaped curve. So for second graders, we could say this test does begin to approach a normal distribution. It discriminates in second grade amongst students who can do really well, students who will do really poorly, with most students clustering in the middle. And the same is true for third grade. That particular graph looks like that as well. Now fourth grade, very interesting. Fourth grade looks not like anything that you've probably that we've talked about so far. It looks like this. It has two humps, two high points, and then obviously three low points. So it looks like almost like a roller coaster. And that's called a bimodal distribution. So what you have is a cluster of scores at the low end and a cluster of scores at the high end, and not too many scores in the middle. There's no average, really. Some students do really well on this test. Other students do really poorly on this test, and not too many students are in the middle, are average on this particular test. So I begin to be suspect about how this test works for fourth graders. It seems to be dividing them up in a curious kind of way. One possible explanation is what happens in fourth grade, which is that we begin to switch from reading to learn to read to reading to learn, or reading content. And some students make that switch pretty easily, and other students continue to struggle with it for a while in fourth grade, and that could explain the Great Divide, if you will. But in any event, fourth grade is a bimodal distribution, and it doesn't look at all like a bell-shaped curve. And then we get to fifth grade. Fifth grade is skewed in the negative direction. It's a negative skew, and that meaning that most of the scores cluster at the high end. Most students do really well on this test in fifth grade, and fewer students do poorly. So for fifth grade, one interpretation might be that this test is simply too hard or too easy for fifth graders. So it's not discriminating in the first grade. It's not discriminating well in fifth grade because it's too easy for them. Second and third grade, the test is okay. Fourth grade, who knows what's going on. So eyeballing it, we would say, I don't know about this test. Maybe I'd use it for second and third graders, maybe, but I wouldn't use it for the other groups. However, I'm a test maker and I'm driven to get this test published, so I don't care what the graphs really look like. What I'm going to do is force these into a bell-shaped curve using the mean and standard deviation. So you all know how to do that. And you could plot a bell-shaped curve for each grade if you want to. You can go ahead and do that. You can plug in the mean and the standard deviation for each grade and look at what the scores would look like for each grade on a bell-shaped curve, which might be fun to do, just so that you could talk about what the score of 8 for a first grader looks like. How far below the mean or how far above the mean is that, because the mean is 7. How far above the mean is a score of 8, and what percentile would that be? Once you've plotted that on the bell-shaped curve, well, you don't even need to plot it. Once you have the mean and standard deviation, you can utilize the z-score. So for that score of 8 for first grade, you could get a z-score. 8 minus 7 divided by the standard deviation of 5.2 would give you your z-score, and then you would know your percentile rank. So you could do that for any of those scores, and for practice before the midterm, you might want to do a little bit of that just to practice. But some of the questions ask you to practice this anyway, and one of the questions talks about Billy. Billy earns a raw score of 15. What would his percentile rank be if he were in the first grade, if he was in third grade, or if he was in fifth grade? So now I'm going to ask you to pause, and I would like you to compute Billy's percentile rank, or z-score, first, and then his percentile rank for first grade, Billy in first grade, Billy in third grade, or Billy in fifth grade. So go ahead. You need to compute the z-score first and then find the percentile rank. So pause and go ahead and do that. Okay, did you compute the z-score for Billy at each of those grades? I did. Billy in first grade, his z-score would be 1.5 if his score was 15. That same score of 15, if he were in third grade, poor Billy, not making any progress, gets a z-score of negative 0.7. And then if he's in fifth grade, he gets a z-score of negative 1.6. So did you get those for z-scores? In first grade, 1.5, in third grade, negative 0.7, and in fifth grade, negative 1.6. And you can convert each of those to z-scores using your chart. So I'm going to look at first grade first. His z-score was 1.5. I find that on my chart, and I see that his percentile rank is 94.3. 93.1 or 93.3. I'm sorry, even with glasses on, my eyes aren't that good, but you can find it. 1.5 go across, it's 93.3. Then looking at his z-score of negative 7 when he's in third grade, I find negative 7 on my chart, and I go across and I see that his percentile rank is 24.2. That's a little clearer. And then at negative 1.6, I find that on my chart. negative 1.6, and his z-score for that is 5.5. Okay, so he's in the 5.5th percentile. So now you know really how to play around with those scores. And now we're asked to prepare a graph for which age equivalents can be derived. Now remember, we don't have scores or grade equivalents. We don't have scores for every grade every month. We have scores, one set of scores for first grade, second grade, third grade, fourth grade, and fifth grade. But I want my test to be usable for kindergarten through sixth grade. So I'm going to prepare a graph, and I'm going to do some interpolating and some extrapolating. Remember, we talked about that. And here's what my graph is going to look like. So you see on the vertical axis, I've listed all the scores, the potential scores that you could get from a score of 1, and I clustered them all the way up to a possible score above 60 even, because that is a range that could occur. That's the range that did occur if you look at our set of scores. And then across the bottom axis, the horizontal axis, I've listed grades, starting with kindergarten and then first grade, second grade, third grade, fourth grade, fifth grade, and sixth grade. And what I did on this chart was to plot or put a dot where each average score was for each of the grades that I tested. And I'm just making the assumption that I'm testing these students at the beginning of each of the grades. So the beginning of first grade, I plotted that score, that average score of 7. So you can see the dot there. At the beginning of second grade, I plotted that average score of 14. You can see the dot there. I'm not going to give, for third grade, I plotted that average score of 20. You can see the dot there. I'm not going to give you the exact average score for fourth grade because you have to compute that for homework. And for fifth grade, I plotted the average score of 46 on my graph. And then I connected the dots. I interpolated the dots. So I connected in between the dots that I had, and then taking the slope of the line, I extrapolated out beyond the dots. So on the low end, I extrapolated from first grade down to kindergarten. I didn't test any kindergartners. And on the high end, I extrapolated from fifth grade up to sixth grade. And I didn't assess any sixth graders, remember. But now I have the potential to guesstimate or even actually calculate if I wanted to. But we're just going to guesstimate for our purposes. I can guesstimate the scores that would give you grade levels in between each of the plotted scores that actually existed and extending beyond those plotted scores. We won't know the actual scores of the students in between the dots, but we're assuming that they're following that trajectory. So now we can go back to that question, what grade equivalent corresponds to a raw score of 2? So if I look at my chart and I look at the x, at the axis that is vertical, I could find where 2 is, which is pretty low. It's between 0 and 5 down there on my chart. I can put my finger roughly where 2 would be and go across to the line that I've drawn and then go down to the spot on the horizontal line. And I can guesstimate that a score of 2 is somewhere early on in kindergarten. And looking at, I've got my horizontal axis divided into 4s, so it's in the first quarter of kindergarten. So roughly kindergarten second month, let's say, would be a fairly accurate grade equivalent for a score of 2. For a score of 8, for example, I can find 8 on my vertical axis, so it's between 2 and 9. Put my finger roughly where 8 would be, and I could actually make a graph that had all these numbers on it, but for the sake of brevity, I grouped them in clusters of 3. Find where 8 would fall, which is just below 9. Draw a line horizontally over to my sloped line, and then go down. And I would find that a score of 8 is slightly above the average score of beginning first grade. So it's in that first quarter of first grade. So maybe it's first grade, first or second month would be the grade equivalent for that score. So now you can go ahead and plot what would be the age equivalents for each of the scores that are given to you on the slide and on your worksheet. Okay, so take a moment and try to guesstimate what you think the scores would be, just to get an idea of how this works. So see, that's simply what test makers do. They interpolate, they extrapolate, and they assume that the scores in between the dots that they actually gathered, the average scores that they actually gathered, the scores in between they assume would actually exist. Maybe they do, maybe they don't. But that's what test makers do. And your final question asks you to characterize a raw score of 15. So I'm going to leave you with that. Think about what does a raw score of 15 mean on this particular test? And whew, we're done with a whole lot of the basic descriptive statistics that go into understanding tests. And in summary, I hope that you understand that there's a number of scores that we use. Those scores are conversions of raw scores. The z-score is the most important score because it enables us to get all those other conversions. And we have formulas for each of those. We have formulas for computing the mean and the standard deviation. You'll need to use that for homework, so you have some practice with that. We've talked about age and grade equivalents, and we're focusing on grade equivalents, but we could have done the same with age as well, getting average scores at various age levels. And our graph would be computing ages instead of grades. We've talked about how we interpolate and extrapolate. We've played a lot with the bell-shaped curve, and I hope that you have an image in your mind of that curve that you'll be able to use to think about students, where they fall. If we get a standard score, knowing where a student fits on the bell-shaped curve. And you have some homework to do to give you some practice with these things. So you have a topical activity for this week's topic. And I'll look forward to next week when we'll be talking more about descriptive statistics, but we'll also be talking about information that's going to be very important for you when you are doing your critique assignment, which is due in several weeks. It's one of your major written assignments. So next week is really important because we'll be talking about all the information that's important to enable you to finish that particular assignment. Reliability, validity, and the normative population is going to be our main focus, but we're going to be talking about a few additional kinds of standard scores as well. So bring your calculator back next week.